Okay. So the goal of our work is to speed up fixed point computation in abstract interpretation by using parallelism while ensuring determinism. That is, we want the same analysis result for every run. Abstract interpretation is a general framework for expressing static program analysis. It infers program invariance by approximating the semantics of programs, and it is used for verifying and optimizing programs. It can be reduced to fixed point computation in the following steps. First, you choose an abstract domain that captures the relevant program properties, and you set up an equation system over this domain to capture the abstract program behavior, and you compute an approximation of the least fixed point of this equation system, and the resulting xi correspond to the invariant at the control point I in the program. So an example abstract domain is an interval abstract domain this can track the range of values of a variable, and as you can see, it has an infinite height. You can set up an equation for this simple code by the following steps. You first construct the control flow graph of this program, and for each control point, for example, control point 1, which is the bottom of the block 1, you specify that with an equation that the value of a is exactly 0. And for control point 2, you say that the value of a is less than 10, and it comes from point 1 and 3. You can do the similar thing for the rest of the equation, and you get the equation system. Now, for this equation system, you can draw a dependence graph, which will be the same as the control flow graph. So what this graph is telling you is that the value of x2 depends on value of x1 and the value of x3. The way you compute this equation system is like this. First, you initialize the values to the bottom, and until there is no change in the values, you update it by applying the corresponding function. So, for example, the iteration order is shown below. You can update value x1, x2, x3, x4, and if you iterate sufficiently enough, you see that none of the values change anymore, and you reach to a fixed point. Now, the iteration strategy, which specify this iteration order and the winding points, greatly affects the efficiency and the precision of the fixed point computation. Again, the iteration order is the order in which the equations are applied during the fixed point computation, and winding points, which is required in general to guarantee or accelerate termination, must cut all cycles in the program. And due to non-monotonic nature of these winding, different iteration orders could lead to a different analysis results, even though you have the same winding point. The state-of-the-art uses an iteration strategy by Bourdoncle. It is based on a notion of weak topological ordering of the dependence graph that we saw. And intuitively, this WTO identifies the loops in the graph and their nesting structures. So again, with the previous examples, its WTO is this, which is just a permutation of the nodes with matching parentheses. The parentheses represent loops. So for this loop is represented in the WTO as this 2, 3 with matching parentheses, and Bourdoncle calls this a component. And to cut all cycles with the winding point, the first element in the component, which is 2 in this case, and is called heads, are chosen as the winding points. And the iteration order induced by this WTO is like this. So you visit 1, you visit 2, 3, and because you reach the end of the component, you go to the head and check the convergence of the loop. One good thing about Bourdoncle's approach is that you only have to check the head to check all the nodes in the loop. If the loop did not stabilize, you continue your iteration over the component. And if the next check succeeds, you move out of the component. Now, Bourdoncle's approach has been implemented in variety of tools. And the advantage of Bourdoncle's approach is that it is deterministic. It has a small set of winding points. It has an efficient iteration order. And it allows you to check stabilization of the loop by just checking its head. The disadvantages are, however, that it is inherently sequential. As you saw, it only allows you to write the total order of the graphs. Also, the WTO construction takes, in worst case, cubic time, and it can lead to stack overflow for deep dependence graph because the algorithm is presented in a recursive way. So our approach to fixed point computation is our approach inherits all the advantages of Bourdoncle's approach and removes the disadvantages. So our approach is parallel, and we have almost linear time construction algorithm for the structure that we use. And it is iterative, so you don't have stack overflows. And furthermore, you get the same analysis result as Bourdoncle's approach. One thing I wanted to stress here is that ensuring determinism and having parallelism was not trivial because of the widening. Because widening is non-monotonic, the change in the iteration order changes the results of the analysis, and So these are our key insights of our approach. We took weak topological order and generalized it to a weak partial order. In particular, WTO is a linear extension of a weak partial order. And the partial order in the WPO allows you to do parallel abstract interpretation. What's more is that we found the connection between WTO and hence WPO and a structure called loop nesting forest, which is commonly found in compiler literatures. By adapting almost linear time algorithm for this LNF to our WTO, we could get almost linear time algorithm for WPO and the WTO. The key theoretical results are as follows. The fixed point computation based on this WPO is deterministic. It has the same precision as Bourdoncle's approach. Our approach guarantees optimal parallelism while ensuring the same result as Bourdoncle's. And we have almost linear time algorithm for WPO construction. And using a linear time conversion from WPO to WTO, we get a new almost linear time construction algorithm for WTO as well. We also made an extensive evaluation on a tool that we implemented called PyCos. It extends the state-of-the-art sequential abstract interpreter ICOS. We evaluated on 1,000 C programs. And PyCos using 4 threads was on average 2 times faster compared to the ICOS. About 52% had speed up greater than 2x, and about 10% had speed up greater than 3x. Sorry. And we also observed up to 11x speed up in PyCos with 16 threads. Our implementation has been pushed to NASA's ICOS, and it is currently being integrated into Facebook Sparta. Now, let us examine some examples of the WPO and see how fixed point computation uses it. So we start with an acyclic graph. The WTO of this graph will just be the topological ordering of the graph. And the weak partial ordering of this graph will be just the same as the original graph. These blue edges that we call scheduling constraints are used for scheduling, not the black edges on the left. And all the predecessors in the WPO has to be executed before a node can be scheduled. For the acyclic graph case, this is just the DAG scheduling. Yeah. And now, if we add these new edges, we get loops in the program. This is reflected by the parentheses in the WTO, which shows the corresponding loops. Now, to express these loops in WPO, we first add something called exits, which are the stabilization checks of the loops. Then we add these red dotted edges to show that there is a loop. The way it works is when the checks succeed in the exits, it allows you to proceed to the successor. And if the checks fail, you iterate over the loops again. And each loop will be iterated in parallel. An interesting situation is when you have dependencies between the loops, like this. This creates dependencies between the two loops. And because 10 has to be executed before 3, you have to flip the order in the WTO, the whole components. However, if the edge was added the other way, this order is fine, so you just leave it as it is. In WPO, one might think that adding the same edge is the correct way, but this actually leads to non-determinism by letting the intermediate values of 8 lead to 9. That is, this 8 is in this loop above, and if the check fails for this loop, it iterates over the loop again, and it invalidates the previous value of 8 by updating it. The correct way is to begin the constraint from the exit 3. Now, this adds a scheduling constraint between the two loops, so it loses some parallelism, but it ensures determinism. The same principle applies for irreducible graphs. So if we added edge like this, it would be an irreducible graph. But yeah, as I said, you wouldn't add an edge like that. You would add an edge from the exit 3. Note that what matters is the source of these constraints, not the targets. So thanks to this, we can execute some part of the loops in parallel. Now, if we add this new edge, we get nesting loops, and we change WTO and WPO correspondingly. Now, interesting situation is when you add this node and the edge. You would put 13 in the right place for the WTO, and for WPO, from the previous lessons, one might add a constraint from exit 9 to 13. But this, again, causes non-determinism, because it still leaks the intermediate values of 12 to 13. This is because this exit checks the stabilization for this nested loop, but 12 is inside this larger loop. So check failure at the x2 will make it iterate the loop again and re-execute 12, invalidating the previous value. So the correct constraint is from exit 2 to 13. Now, we have seen that adding these constraints to require some considerations, like this, yeah. In general, scheduling constraint should begin from the exit of the outermost loop containing the source, but not the target of an edge. To do this, you must find the outermost loop containing U but not V during the WPO construction for a dependence UV. This relates to finding the lowest common ancestor of UV in the loop nesting forest. And what this achieves is that for dependence UV, unstable values of U are never used when updating V, XV. Again, I reiterate the key theoretical results. We have deterministic parallel fixed point algorithm. It has same precision as Bourdoncle approach, and it has optimal parallelism while ensuring this. The details are in the paper. Now moving on to empirical evaluation. So we have implemented our approach in a tool called PyCos, which extends the WTO-based sequential abstract interpreter, ICOS. It inherits all the existing abstract domains in the widening narrowing strategies. And we have evaluated PyCos using 1,000 C programs and then using interval abstract domain. So this was interprocedural analysis. And 500 programs came from SVComp benchmark, and 500 came from official Arch Linux core package. You can see the paper for more details about the benchmark selection. So as our first question, we empirically validate the theoretical claims. PyCos was, yes, deterministic, and it had the same precision as ICOS. We also studied the performance of PyCos 4, which is PyCos with 4 threads. We measured the speed up. This is higher the speed up is better. We show the result on a log-log scatter plot in which y-axis shows the analysis time of PyCos 4, and the x-axis shows the analysis time of ICOS. So this y equals x solid line shows no speed, the same speed, and the ones below this solid line implies that PyCos 4 was faster than ICOS. We had geometric mean of speed of 2x, and we had a maximum speed of 3.63, where 4 is the maximum possible speed up. Okay, PyCos 4, yeah. 52 had greater than 2x speed up, and 10% had greater than 3x speed up. Yeah. And PyCos 4 exhibited higher speed up on programs for which ICOS took longer. And if you plot the histogram of the speed up of PyCos 4, for programs for which ICOS took more than 500 seconds, you could see that the average went up. Now, we also looked at scalability. Here, we just show the top 5 benchmark with threads 4 to 16. But you can see more details in the paper. In particular, this benchmark had 11x speed up with 16 threads. This benchmark contained this function, which is called multiple times in a loop. And ICOS spent most of the time in it. And PyCos could exploit this parallelism in this graph. So to conclude, we present a deterministic parallel fixed-point computation. It introduced the notion of weak partial order, which generalizes Bourdonque's WTO, and it's almost linear time construction algorithm. This WPO-based fixed-point algorithm exhibits optimal parallelism while computing the same result as the WTO-based one. The code is available on GitHub, and it is integrated into NASA ICOS, and we are integrating it into Facebook's Sparta. Thank you very much.
We have about 30 minutes for questions. Okay. Well, okay, I said we have 30 minutes for questions, but we should not abuse it. Okay, Josh.
Hi, thanks. Can you say anything about the representation of the partial order relative to what you normally have for the WTO? I mean, I guess you can't just use a numbering anymore, and you might have some space overhead.
Yes. You mean in the implementation, right? So we have for each node we have vector of nodes which have maps to the successors and the metadata required for doing the fixed point computation. Yeah.
Okay, so there is a question from the Slido. So the question is whether the speedup is coming from the fact that most practical program control flows don't have non-reducible loops.
Sorry.
So the question is whether the speedup comes from the fact that in practical control flow graphs, there is no non-reducible loops, or very few of them. In which case, essentially you have sequential computation anyway.
So one of the key theoretical results of our paper is that we have optimal parallelism for the while ensuring the same precision as Bourdoncle. So if the program doesn't have a branch, or if it's just sequential, you won't have any speedups there. If that's the question that was asked.
So I have another question, which is regarding to another approach to building abstract interpreters, where instead of trying to build control flow graph, you use abstract syntax tree and define essentially compositional abstract interpretation function. So I guess my question would be, how would you compare approaches like yours to this one, where, for instance, opportunities for parallelization come up directly from the control flow, from the abstract syntax tree of the program?
Okay, so the main assumption of our approach is that you have control flow graph statically upfront. We haven't compared with other. I thought of comparing it with abstract syntax-based approaches, and I think it's interesting future work to compare them. Yeah.
Okay, that's fair enough. Any other question?
So in the experiments, you compared the instantiation for 4 threads to the baseline. So did you also experiment with another number of threads?
Sorry, could you repeat that?
So did you also try like 8 threads or 2 threads? And so why did you choose 4 threads for your experimental comparison?
Yes, so we tried on 1 thread, 2 thread, 4 thread, 8 thread, and for the top 5 benchmark in the slides, we also tried 12 and 16. And the result, the 4 threads seem to show the distribute. Yes, we read on 2468. Yeah. Sorry.
Okay, so unless there is a last question, I would like to thank again Kook for the great talk. Thanks.